Hey everyone, and welcome back. This week we're going to review some of the fundamental and important concepts around representing substances, so writing formulas, balancing, writing formulas, naming compounds, and then how we represent chemical changes and chemical reactions, so balancing equations, classifying reactions. We are going to start with kind of looking at and reviewing those rules for writing equations, for naming compounds, writing chemical formulas. Remember, you need some tools. You need your periodic table. You need your flow chart. If you lost them, go to your teacher's Canvas page, print one out, or open the file. Okay. So first thing we're going to look at and kind of review the rules for naming compounds. And then we'll look at some examples, and we'll look at the rules for writing chemical formulas, look at some examples, and then kind of look at reactions. So you have one of these naming compounds flowchart. Remember, there are three kind of types of substances. There are ionic compounds, molecular compounds. And for us, we do the simple binary molecular compounds, and acids. We're going to start off with the ionic compounds because naming ionic compounds, they have the most rules that you have to worry about and the most parts that you have to worry about, okay? And so when you're looking at identifying what type of compound it is, that's the first step. You need to think, right, sometimes it's easier to kind of rule out everything except ionic, okay? So for things like binary molecular compounds, okay, where you're just going to have two elements and they're going to be two nonmetals. Okay, so if you see a substance with two nonmetals, it's a binary molecular compound. Okay? It's going to have its own set of naming rules. If you're looking at the compound and the first element is hydrogen, it's going to be an acid. They are going to have their own set of naming rules. Okay, so rule those out first. Look for hydrogen as the first element, with the exception of water. If you see it, it's an acid. It has its own set of naming rules. If you see a compound that has only two nonmetals, okay, it's a binary molecular compound. Has its own set of naming rules. Anything else is ionic, and gets named as an ionic compound. And so we're going to go over all those other combinations that are not substances with just two nonmetals, that are not substances that, besides water, whose first element is hydrogen. Okay? And so, when we're talking about those ionic compounds, right, the simplest type of ionic compound are the binary ionic compounds. Right? The ones that have a metal and a nonmetal. Right? So we have those binary molecular compounds, metal and nonmetal. Okay? So if you look at our periodic table, right, we see that we have the simplest type. We have metals. So right, remember, these are all our metals. Okay? We have nonmetals, opposite ends of the periodic table. Easiest type of ionic compound. Okay? Now, whenever we're going through to name an ionic compound, you always have to name the cation and name the anion. If it's a simple binary ionic compound where it's just a metal and a nonmetal, and the metal is not a transition metal, right? So if we have the metal as the first element and it's not a transition metal, we're down here, we name the metal first, look up the periodic table, find the metal, we name the nonmetal, and we have to change its ending to IDE. Okay, so when we look at those nonmetals, so let's go back to our periodic table. If we look at those nonmetals, right, fluorine, chlorine, bromine, iodine, right, when they're in an ionic compound, they're going to be the anion, negatively charged ion. Right? their endings get changed to IDE. So chlorine, for instance, you would drop the INE in IDE, so chlorine becomes chloride, fluorine becomes fluoride, right? Iodine become iodide. Some things like sulfur and oxygen and phosphorus, right? Those nonmetals, when you drop their endings, you're either going to have to drop more, like phosphorus becomes phosphide, sulfur, you actually have to not drop it. You're only dropping the UR, it becomes sulfide. Oxygen, you drop a lot, it becomes oxide, okay? So when we're kind of talking about those ionic compounds, we have, all right, it's a metal. Right? Is the metal a transition metal? It's not. It's the simplest type of ionic compound, right? Name the metal, and then name the nonmetal. And change the ending of the nonmetal to IDE. Now, if the metal is a transition metal, that's when you have some things you have to worry about. Because if it's a transition metal, remember where the transition metals are. Transition metals are these substances that are, right? These substances here are transition metals. These metals, plus metals like tin and lead, are polyvalent. Remember, that means they can form more than one type of ion. And so if you have a metal that is a transition metal, or tin, lead, and so the metals down below here, these metals, when they are in a compound, you need additional information. You need to indicate the charge of the ion that they are in that compound. And the way we indicate that charge is we use a Roman numeral. And so let's look at some examples. So if we look at some examples, right, Fe down here, PbI4, okay, lead, it's not a transition metal, but tin and lead, again, one of those ones we just mentioned, are polyvalent. Lead can have a couple of different ions that it forms. So we need to indicate what specific ion we have formed in this compound. And so we have to figure out what the charge of the lead ion is, right? So we kind of have to work backwards. So I, right, is iodine, or in this case it's iodide because it's the ion. It's in group 17, so it has a -1 charge. Now there are 4 of them, which means there are 4 minuses charges in this compound. Ionic compounds have to have a balance of charge, so we need 4 positives. Now, it happens that there's only 1 lead ion. How do I know? Well, if there's no subscript, it's a subscript of 1. Because there's only 1 lead ion, that means that 1 lead ion has to have a charge of +4. And so the name, we need to include a Roman numeral that indicates the charge. So this is why it's lead 4 iodide. That Roman numeral is the charge of the lead in this compound. And anytime you have a transition metal, so anytime you have a transition metal, or you have tin and lead, and there's a couple others that are on your flow chart, you need to include a Roman numeral in the name, so you need to figure out the charge like we just did. Okay. If we go back to our flow chart, okay, and we say, all right, is there a metal? And if there's 3 or more elements that we have, then we have what's called a ternary ionic compound. Ternary ionic compounds may have a polyatomic ion in their formula. And so remember, you have a list of polyatomic ions on your flow chart that you were given, but here's a list here. Okay. Now notice many of these polyatomic ions end in ate or ite because they contain oxygen. Some of them don't, like ammonium. Okay, but you can have ionic compounds with polyatomic ions, and they're ternary ionic compounds because they have 3 or more elements. And so when we recognize them, if there's more than one of the polyatomic ion in the formula, it'll be in parentheses, like this one, makes it easier. This means there's 2 of these nitrate polyatomic ions. Sometimes if there's only one, you're not going to see the parentheses, like in the sulfate. And in that case, right, look for the two capital letters side by side, right? And so SO4, look on your table, and we'll see what sulfate is. So if there's a polyatomic ion, right, if the first element's a metal, if it's not a transition metal, then you just name it, and then you name the polyatomic ion, no ending changes. If the first element is a transition metal, then you need to figure out its charge, just like we did, work backwards, and include a Roman numeral after the metal. So this is iron 2 because iron has a +2 charge, and then name the polyatomic ion nitrate. Again, notice no ending changes. You can have a polyatomic ion or an ionic compound that has two polyatomic ions, right? You'll recognize these because there's often a whole bunch of nonmetals strung together, and we can't name anything but basic binary ionic compounds, so they can't have more than two ions. So that means, in this case, look for the parentheses again. So in there is a polyatomic ion, NH4 is ammonium, PO4 is phosphate. So we put them together, ammonium phosphate. One exception, there are some transition metals that are not polyvalent, like silver, it's just +1. There's a couple others that we've wrote on your periodic table. So notice, even though it's a transition metal, that exception, again, they should be written in on your periodic table, right? They do not have a Roman numeral. Okay. The other possibilities, again, we talked about binary moleculars at the beginning. If it's two nonmetals, it's a binary molecular compound. So they have a different naming system. Those binary molecular compounds use prefixes. Again, the prefixes are listed on your flow chart, so pull that out. The prefix indicates the subscript in the formula. You always use a prefix except when the first element has a subscript of 1, you don't use the mono prefix. Any other time you do. So again, this would be nitrogen tri for 3 chloride. Okay. Boron trichloride, and so on. Notice that the second element always gets its ending changed to IDE all the time. Okay, dinitrogen trioxide. So again, the only time you don't use a prefix to indicate the subscript is when the first element has a subscript of 1. If the second element has a subscript of 1, you'd most certainly use the right prefix. So for instance, NO would be nitrogen monoxide. So we use that mono prefix to indicate there's one oxygen, okay, and change the ending. So an acid, the acids that we can name are organic acids. Again, they always start with hydrogen. Okay, always the first element. The only thing that's the exception is water. There are two. There are binary acids, right? Like H2S. These always start with hydro at the beginning of the name. They always end in the word acid, and then you have the root of the non-metal element. So that's why this is hydro. Sulfur becomes sulfuric acid. Okay, HCl would be hydro. Right? So if we had HCl, right, HCl would be hydro. The root of the element, chlorine, is CHLOR, so hydrochloric, and then the word acid. If you have a ternary acid, so if you have an acid that has 3 or more elements, it contains a polyatomic ion. The name of the acid is derived from the polyatomic ion. Most of the polyatomic ions contain oxygen. So you name the polyatomic ion. SO4 is sulfate. If the ending of the polyatomic ion is ATE, you change it to ICE, so sulfate becomes sulfuric, and then add the word acid. H2SO3, SO3 is sulfite. If the polyatomic ion ends in ITE, you change the ending to OUS, so sulfite becomes sulfurous acid. HNO3, NO3 is nitrate. Again, ates become ic, so nitrate becomes nitric, and then add the word acid, so nitric acid. When you are writing formulas, you're going in reverse. For ionic compounds, right, you need to identify the cation's always first, the anion is always second. You need to work backwards. So you need to write the formula for the cation. So magnesium is Mg. If it's not a transition metal, you're going to have to look at your group numbers and look at the common ion charges for the different groups. If it's a transition metal, you're going to look at the Roman numeral to get the charge. Okay, if it's a polyatomic ion, because there is a polyatomic ion that's a cation, ammonium, look at your flowchart. Write the charge. Look at the anion. If it's a nonmetal, it's going to end in IDE with the exception of like 2 or 3 polyatomic ions. So you're going to have to find the nonmetal and then look at the group to figure out the common ion charge for the nonmetals in that group. So chloride is chlorine. They form -1 ions. And then you need to figure out, all right, you need a balance of charge. You need the same number of positive and negative ions. So in this case, we have a +2 and a -1. If you think about that, think about least common multiples, right? 2 times 1 is 2. So the least common multiple to 2 and 1 is 2. So we're going to need, in order for the charges to balance, we're going to need a total of 2 positive charges and 2 negative charges. Well, we already have +2. In order to get 2 negative charges, we're going to need 2 minuses. So that means we're going to need 2 of the chloride ions. So our final formula, the subscripts will reflect the number of ions that we need in order to balance the charges. So we need 2 chloride ions, so we get MgCl2. If we have something like aluminum oxide, where we have aluminum, which is in group 13 and with the +3 charge, and oxide is oxygen, and they form a -2. We need a balance of charge in the chemical formula, so we have a +3 and a -2. Well, 3 times 2 is 6. So in order to have a balance of charge, we need to have a total of 6. So we need 6 positives and 6 negatives. Well, to get the 6 positives, we're going to need another aluminum to get a total of +6 positives. And we're going to need 2 more oxide ions to get a total of 6 negatives. Right? And so here's the combination that gives us our balance of charge. We have +6 and -6. So our formula is going to be Al with a subscript of 2, O3. Right? If your ionic compound is a polyatomic ion, you need to remember that those polyatomic ions, if there's more than one, you need to put the subscript. The polyatomic ion has to go in parentheses, and the subscript goes on the outside. Okay, so if you're writing the formula for a binary molecular compound, you need to just translate the prefixes into subscripts. So if there's no prefix, it's a 1, and then translate the prefixes into subscript and the element names into their symbols. Okay, remember, these are binary molecular, they're not going to have more than 2 elements. If you are writing the formula for an acid, remember the cation, they always start with hydrogen and it has a +1 charge. Okay, you need to figure out what the anion is, so that the charges balance out. So if it is an oxyacid or a ternary acid like carbonic acid, you change the ic to 8, so carbonic becomes carbonate. Look up that polyatomic ion, it has a -2 charge. Hydrogen is always +1, and so we need H2CO3, right? Balance of charge. Chlorous acid, OUS, came from ITE, so chlorous was the chlorite ion, so we looked that up on our flowchart. In this case, we have a +1 and -1, balance out. Hydrobromic, binary acid, starts with hydro, so bromic is going to mean bromide ion, which is -1, or bromine, and right, bromide ion, -1, group 17. Hydrogen is always +1, 1 of each, HBr. Now, if we kind of take a look, we take these, right, and we look and say, all right, we can represent chemical changes and chemical reactions by putting together the chemical formulas, and we can get chemical reactions, right? And there are some, because there are so many different types of reactions, in order to really study them, chemists will often classify them. And so we talked about 5 reaction types, right? Single synthesis, decomposition, single displacement, double displacement, and combustion. Sometimes either single replacement and single and double replacement. But synthesis, you're making something, notice the pattern, okay? You have a bunch of reactants and you're forming one product. Decomposition is the opposite. You have one reactant breaking down into more than one product. Single replacement or single displacement is element plus compound, and you get a new element in a new compound. And so that element can be a metal replacing the cation in an ionic compound, or it can be non-metal replacing the anion in an ionic compound. And if that replacement happens, you get a new compound in a new element. Double replacement or double displacement, you have ionic compound and plus ionic compound, and you're forming 2 new ionic compounds. So the big thing for a double replacement or double displacement is that the cations trade partners to form new ionic compounds. And these are the ones that we talked about as precipitation reactions. Combustion, right? You need a fuel, you're burning stuff. Generally, it's a carbon-containing compound. You'll always have oxygen as your second product. And so you always have to put that in. And then, if it's a complete combustion, you get carbon dioxide and water, right? As well as heat. Now, if we take those reactions that we've classified, remember, reactions have some basic parts and properties that we have to worry about. And so, remember we have symbols, right? We have the plus sign, the arrow that means yield, S, L, and G are states of matter, solid, liquid, and gas that get written after the formula. AQ indicates that the substance is aqueous, so it forms a solution, it dissolves in water. The Greek letter delta, or heat, means that heat is needed. If you see the formula above the arrow, it means there's a catalyst that is needed, okay? And so remember, when we kind of look at those reactions, they have to obey the conservation of mass, which means we need to balance those chemical equations so that they obey the conservation of mass, and so that the number of atoms on the reactant side and the product side equal up. So if we look at this example, right, this is a kind of a combustion of this fluorine compound, where you're getting carbon monoxide, water, and fluorine gas probably. So list the elements and then count up the number of each element on either side. So in this case, we have 6 carbon atoms, 5 hydrogen atoms, 1 fluorine atom, and 2 oxygen atoms. And then on the product side, we have 1 carbon, 2 hydrogens, 2 fluorines, and 1 plus 1 is 2 oxygens. When you have something with oxygen, especially these kind of combustion reactions, leave the oxygen to last, okay? Because often you'll have to change them because they're 2 things. So do the carbons, the hydrogens, in this case the fluorine first, get those to balance, and then worry about the oxygens. So that's why, if we do the fluorines first, because we're going to have to change this coefficient, we're going to have to put a coefficient of 2 in front of this so that we have 2 fluorine atoms. And so remember, that coefficient distributes to everything in the compound. So that means we're going to change the number of carbons and hydrogens as well on the reactant side, okay? And as well as the fluorines. Now, we can get the carbons to balance out because now we have 12 carbons, so we're going to have to put a 12 in front of the carbon monoxide. That's going to change the oxygen, so we'll add those up last. We're going to need 10 hydrogens, so we're going to have to put a 5 in front of the H2O. Okay. And then the fluorine is fine because those are balanced right now. So, we can put a 1 there if we want to. Okay. Now let's do the oxygens. Right? If we look, we have 12 plus 5 gives us 17. Now we have 2 on the reactant side. So 2 and 17 to go into an even number. But we can kind of figure out, all right, fractions, right? 17 halves, right, times 2 would give us 17. So technically that would balance our reaction, but we can't have this fractional coefficient. They have to be nice whole numbers, and the simplest whole numbers. So we need to take this and multiply it by 2 to cancel out that half. But we have to make sure we do everything by 2 so that the reaction stays balanced. And so that gives us kind of our final answer down here. Okay, when you're looking at reactions and kind of going to balance the reactions, a couple of tips and tricks. Make sure you're adjusting the coefficients and not the subscripts. If you have an odd, kind of even odd numbers, try to get them even. So for instance, this zinc sulfide and oxygen example, we have 2 oxygens and then we have 2 plus 1, we have 3. So we have an even number on the left, but an odd number on the right. So first start off by adjusting the coefficients to try to make the right side add up to an even number. So if we put a coefficient of 2, now we have 2 plus 2 gives us 4. And just doing that often makes it easier to balance everything else out because things start falling into place a little bit better. Right? If you have a polyatomic ion, like nitrate, that appears on both sides, you can kind of count this as a group instead of individual atoms, and it just makes the counting easier. So you can count this as 2 nitrate ions and 1, because no parentheses, nitrate ion. Okay? And it just makes the counting easier. Okay? Now, when you are actually going to balance, we need to remember that, when we change those coefficients, that those coefficients are representing particles. So if we have a coefficient of 1 in front of everything, that means we have 1 molecule of SO2, 1 molecule of H2, 1 molecule of H2S, and 1 molecule of H2O. Okay? And so if we're trying to balance these out, right, notice that right now we have the same number of sulfur atoms. We have the same number of hydrogen atoms. Sorry, no, we don't. We have the same. We have 2 hydrogen atoms here, and 1 plus 1, or 2 plus 2, 4 hydrogen atoms on the other side. And we have 1 oxygen in red and 2 oxygens here. So what do we want to do first? Okay. Well, let's just start somewhere. Let's start trying the hydrogens first, or the sulfurs first. Sorry, not the sulfurs. Yeah, the hydrogens first. So we have 2 and 2. Okay, is 4. We have 2 on this side, so we need to add another molecule. Now, okay, what does that do? Hydrogens, now we have 1, 2, 3, 4. We have 1, 2, 3, 4. So the hydrogens are good. Sulfurs are good. Oxygens, not good. All right, we have 1 here and we have 2 here. So the only way to increase the number of oxygens is to add another water molecule. Okay, now what did that do? We have the oxygens were fine, but notice that also changed the number of hydrogens. Okay, and so this kind of brings us to a point. Because hydrogen appears in 2 different places on the products, it's probably a good idea to leave it till last. That's why we often leave oxygen till last, because especially in combustion reactions, it appears in 2 different places. Okay, and so because in this case, in balancing the oxygens, we also change the hydrogens. Now in this case, we need 2 more hydrogen atoms, so if we add another hydrogen molecule, that will balance things out, and this should check out. There we go. Okay. So, as we're kind of going through and balancing those reactions, remember those coefficients represent particles. Okay. And if you find yourself stuck, just start over, but start over from a different spot. Okay, and if you see something where you have a substance where it appears in one place on the reactants but two places on the products, try leaving that substance till last. Okay, try the lab, the virtual lab. Stop by your teacher's office hours if you have questions, and have a great week.